It is my pleasure to introduce Professor Chris Reynolds, who is a professor in the Department of Astronomy at the University of Maryland in College Park. He received his PhD from the University of Cambridge in 1996, working with Andy Fabian. After graduating, Chris spent 5 years at the University of Colorado, including 3 years as a Hubble Fellow, before joining the professional faculty at the University of Maryland in College Park in 2001. Starting in 2017, he spent 6 years at the University of Cambridge in the UK as the Blumian Professor of Astronomy and Experimental Philosophy, but returned to the faculty at the University of Maryland in 2023 to become the director of the UMD NASA Goddard Space Flight Center Partnership of the Joint Space Science Institute, JSI, and to become also the principal investigator of the AXIS mission. So today, Chris will discuss AXIS, and we're very, very happy that he took some time to come here and introduce us to AXIS. So Chris, thank you for accepting our invitation, and take it away.
Thank you. Okay, is this working? Good. Thank you, Julia. It's a huge pleasure to be here. Thank you for the invitation. I would say that my 6 years in Cambridge, one of the best things that came out of that was to work with fabulous students, and Julia was one of the most fabulous. So, it's great to be back at CfA. It's been too long since I've been here. I spent many a happy day in this room, especially as part of the Chandra Users Committee many years ago. And so it's great to be here. So I want to give you an introduction for those of you who haven't heard me talk before, and a status update on AXIS, the Advanced X-ray Imaging Satellite. So I certainly don't. Why isn't this working? There we go. I don't need to remind this particular audience that it was now more than 25 years ago that the Chandra X-ray Observatory launched, and this beautiful nighttime launch, which I'm still mad with myself for not going to. And this fundamentally transformed not just X-ray astronomy, but astronomy. I mean, again, this audience knows this better than any audience in the world. That Chandra really brought X-ray astronomy to the table of mainstream astronomy. Every aspect of astronomy was touched by Chandra, from studies of literally the planets on our doorstep, out to the AGN in the distant universe. So I'm not going to run through all of these. You'll recognise, or certainly many of these images. And Chandra continues to do great work today, and especially, for example, through its legacy programs. And I'm part of the Perseus legacy program, which is going on right now. The current Perseus data is 1 megasecond, and is still, at the smallest scales, is still photon starved. We can't really pull the physics apart at the PSF that Chandra is capable of, because of lack of photons. So that's the goal of the legacy program, is to really burn in Perseus much deeper and learn about AGN feedback, learn about cluster physics. And so Chandra continues to do great work. And I say from the bottom of my heart, may it continue to do so for many, many years. And let's all fight the good fight to make that happen. But many of us have been thinking a long time about what's the next big thing after Chandra and its compatriots, XMM and the other satellites, wrong way. And many of us in this room were lining up behind Alexei several years ago with the LYNX concept, which was the flagship X-ray mission that was considered by the Astro 2020 Decadal Survey. And of course, first and foremost, we need a bigger telescope than Chandra. Chandra, is an exquisite telescope, but at the end of the day, in many respects, it's photon limited. Its effective area limited. Its effective area is relatively small. So that next big step must include a big step in the size of our telescope, the effective area of the observatory. So just to remind you of links. So links, the idea was a half arc second, so Chandra quality PSF with 2 square meters and an array of instrumentation, but including a microcalorimeter, so high resolution spectroscopy. So 2 square meters of area brought to bear on microcalorimeter. We can only dream about what that would mean. And those of you who are involved with GRISM now can see the power of microcalorimeter spectroscopy, even with a small telescope. Now, of course, LINX wasn't to be, unfortunately, not in the last decadal survey, and this was the results of the decadal survey. The next big flagship that was approved was, of course, at that time called Louvois. So now it's become Habitable Worlds Observatory, a truly ambitious infrared optical UV flagship that is slated to launch in 2045. And while the decadal survey actually did, in some sense, approve other missions, it put them into a sequence that follows Louvois. So those of us who, apart from the youngest people in the room, have to worry about hitting the retirement age before that point. But the decadal survey did recommend, one of their major recommendations was a new line of missions, the probe class missions. So it was recognised that at the $1 billion mark, so less than a flagship, but much more than the regular Explorer class missions, at the $1 billion mark, the decadal survey actually said $1.5 billion, that you can do some really important transformative astrophysics. And the decadal survey explicitly recommends that the first probe be either an X-ray probe or a far-infrared probe. So, of course, many projects, many teams went off and started developing mission concepts. In some ways, many of them you could think of as taking aspects of LINX and sort of pulling it apart into its different dimensions, into the spectral resolution dimension with LEM and ARCUS, into the imaging dimension with AXIS, and they were all fabulous missions. So the fundamental philosophy for AXIS was born in 2016 from Will Zhang's next generation X-ray optics lab. Fundamentally, what you want to build, take the next big step beyond Chandra, you have a problem, which is that X-ray optics, of course, are grazing incidents, and they have to be extremely exquisitely polished. But because they're grazing incidents, you need large areas of and so, Chandra achieves this by having exquisitely polished optics, but quite thick and heavy to keep their form. Well, to make a viable mission that does, say, an order of magnitude better than Chandra, you need much lighter mirrors. You need it much cheaper than Chandra. And so the breakthrough from the Goddard Next Generation X-ray Optics Lab was to find the right substrate that we needed. And the current substrate that they're using is single crystal silicon mirrors. So the idea is that you can buy literally macroscopic blocks of single crystal silicon from the semiconductor industry. It's the same material that the semiconductor industry would then slice into wafers to make high quality silicon chips. But we slice it up into segments of mirrors, which we polish, and because it's all single crystal silicon, it's a very stable substrate with no internal stresses. So this was the basic enabling technology for the AXIS mirror. And the AXIS concept is the biggest and best mirror we can make with this technology, with a very capable but mature detector at the back. So that's the driving idea of AXIS, the biggest and best mirror we can build, and get that on the sky for the $1 billion. Okay, so a little bit of the history of AXIS, just how this is turning into a real project. So I say that basic concept was 2016, that we've now got this technology. or burgeoning technology that's turned it into a mission. We had the first Access team meeting in 2017. This is the group there. Hiding at the back, you can see Richard Shotsky, who is known to many of us, and a colleague of mine from UMD now. He was a civil servant at Goddard for the longest time. Richard was PI, became PI of this team, and was PI of the team through the process of proposing its decadal survey and passed that process. So we wrote a concept paper for the decadal survey, and this was one of the many concept papers that basically promoted the idea of a probe-class mission decadal survey. Decadal survey, as we just saw, adopted the idea of this probe-class mission, and then so we're off to the race was started, and in November 2023 we submitted the step 1 proposal. And I became PI of the project when we were working up the step 1 proposal. Okay, so what I'm going to do today is tell you about the basic characteristics of Access. I want to just highlight a few of the science cases, just try to whet your appetite about some of the science that it can do, and then give you as much as possible, give you an open, transparent update on where we are in phase A, and hopefully you can see that I think we're in a good place. Okay, so this is the basic parameters of Access. I'll show you a table of numbers that might be more digestible for you in the next slide. But the idea is that we have our baseline point spread function is 1.5 arc seconds on axis, and then has a very gradual degradation as we go off axis because of the optical design of the mirror. So of course on axis we're inferior to Chandra, but we have a much larger field of view that keeps a point spread function below two arc seconds, half power times compared to Chandra. Matched with that is a much larger effective area. So these are our baseline effective area curves. So at peak, around about 1 kV, we're just about 4,200 square centimeters. This is our baseline. Our current best estimate is actually 20% above that. And coupled with that, we actually also have a fast reaction ability. So often I talk about Access as being the next big evolution beyond Chandra. It's also, in some sense, the next big evolution beyond Swift, because it has the ability to chase down transients and actually also be the original source of transient alerts in a similar way that Swift does. And I'll talk about that in a second. So with these capabilities, we can now stand toe-to-toe with the major facilities that will be operating in the 2030s. This sort of horizon plot, this is an attempt to show the horizon at which we can do various studies, both galactic and extragalactic. And you can see that, let's focus on the extragalactic, that we can study AGN, for example, out to redshifts of touching 10, which puts us toe-to-toe with what JOST can do with LISA detections of merging black holes at those redshifts. So we can now get X-ray astronomy back to the table of that very high redshift black hole work. Galaxy clusters, we can look at galaxy cluster physics out to redshift of a few, which again gets us back at the table with what Roman can do and with the next generation radio studies, the SC studies. And in the neutron star mergers game, this Access well exceeds the horizon that would be related, that is relevant for LIGO or for Rubin. So this gets us back to the table of where 2030s astronomy will be with X-ray capabilities. So this is just a few numbers if you don't read those graphs. Again, signature numbers here are our baseline values. So by baseline means we hope we can do better. The expectation is we can do better, but this is where we draw the line and say failure would be to fall below that. These are effective areas, so depending upon the energy, it's roughly 5 to 10 times Chandra. Usable bandpass 0.3 to 10 kV. We are striving to maintain soft X-ray sensitivity, because so much of the science we're interested in is soft X-rays. So when we put 0.3 there, we mean 0.3. We are striving to have soft X-ray capabilities. Of course, with such a large effective area with a good point spread function, we need a fast detector. So conservatively, we're saying faster than 5 frames per second. The detector is next generation or next evolution of the detectors on ASIS. So the MIT Lincoln Lab CCDs, and our MIT colleagues say that we should even conservatively expect to be able to get 20 frames per second out. So that's good there. I'll talk about the orbit a little bit later, but our baseline is Sun Earth L2 halo orbit. And these other numbers are 5-year prime mission, high observing efficiency, and the launch date of 2032. Okay, now I want to try to not speak for the full hour, so there's lots of time for questions if you've got any questions about this. Right, let's quickly jump into the science of Axis. So the science program, and this is laid out by the announcement opportunity, this is defined by NASA, is that there are two sides, two facets to the science program of Axis. There's the PI-led science program, and this is the program which we have to lay out in gory detail in our proposal, in our step 1 proposal. Then we've got to flesh it out in our concept study report that is due later this year. This will be the science case that will generate most of our formal level 1 requirements for the observatory. So in other words, this is the one that NASA judges, are you going to pull it off or not? And are you selectable or not? So the PI-led science program, we're focused on 3 pillars, 3 of the 4 pillars from the Cable survey: supermassive black holes, particularly what seeds them at high redshift and how do they grow once they're seeded. Galactic ecosystems, how do baryons cycle, both gas, metals and dust, cycle in and out of galaxies, and then the time domain, particularly the diversity of stellar explosions, diversity of explosive phenomena. So I'll dig into each of these in a minute. But then the whole other side to it, that's only 30% of our observing time. 30% of our observing time is for the PI-led science program. The other 70% is general observer science. So it's the community. And there's just a pie chart showing that. So it's in a very important major way. We are actually designing an observatory for the community. Most of the time is community time. And will be allocated through the usual peer review process that NASA will run. We don't run that. NASA will run and fund that. Okay, so in terms of science, of course, one of the defining characteristics is the sensitivity curve. So this is the predicted sensitivity curve for Axis. So the time on the bottom is in units of kiloseconds. So 1 kilosecond is there, 1 megasecond is up there. And of course, your flux sensitivity depends upon the spectrum of the source you're looking at. So we've got two sets of lines here, one for a power law source, think AGN, and one for a black body source, think either a very, very soft AGN or a stellar corona. And the key thing is that we can drill down to 10 to the minus 15, flux of 10 to the minus 15 within, depending on the spectrum, a few kiloseconds, so some number of kiloseconds. We can drill down to 10 to the minus 17 in, depending upon your spectrum, less than a megasecond. And at the deepest fields you can imagine driving deep fields out to 7+ megaseconds. In the deepest fields you can get down to a few times 10 to the minus 18 in flux, which is a factor of several better than Chandra can do in its deepest field in the most sensitive parts. So this is a simulation. I'm glad the lights are down a little bit because this can look terrible. in a well-lit room. But this is a simulation of the Axis 7 megasecond deep field, and in this simulation, there's about 10,000 sources. This is one field. This is 124 arc minute chunk. There's about 10,000 sources, which might even be conservative, and about half of those are AGN, and about half are galaxies. It's the X-ray binary emission in galaxies. And then, of course, we've dropped a few galaxy clusters in there, the big splodges. So one of the key science problems that is driving the PI-led science case are very high redshift AGN and the seeding of supermassive black holes. Of course, this is a field that's been evolving tremendously rapidly in the past year with JWST, even since we submitted the proposal. So, one of the challenges we have in Phase A is to somehow keep up with this field. But the basic problem, the basic astrophysics problem, is how do you get supermassive black holes today in galaxies? So this is time running from Big Bang at the top down to present day, and black hole mass increasing left to right. So today we know we've got very massive black holes that sit in most galaxies. How do they get there? And broadly, the theorists are now beyond this simple characterization. But broadly, you've got two scenarios: a heavy seed scenario, where some monolithic collapse process in protogalaxies can, if you can prevent fragmentation of the gas in the core of a protogalaxy, then it can collapse in one go to a 10 to the 6 solar mass black hole, and then that grows as up to the monsters we have today. Or the light seed scenario, where you have POP3 stars which end their life as maybe 100 solar mass black holes and then grow quickly to produce black holes of today. These give you fundamentally different predictions in the luminosity function of AGN at very high Z. And some of the best predictions come from Angelo, who's sitting in the back there. And this is from his paper in 2018. And you can see that even out to, so the lines here are for light seed scenarios and heavy seed scenarios. And you can see that even out at redshifts of 8 or so, the luminosity functions are pretty similar, not really distinguishable. It's when you get to redshifts of 9 and 10 that the predicted luminosity functions of light seeds and heavy seeds really start to diverge. In other words, the light seed scenarios at a redshift of 10, those light seeds just haven't really had much time to catch up and form luminous AGN at that redshift. So this is the redshift you need to be really doing your luminosity function work at. And Axis is tuned to be able to do that. So I'm going to skip to this one. So these are luminosity functions by deep surveys at redshift 8, 9, and 10. You see at redshift of 10, in the light seed scenario, we should see nothing. In the heavy seed scenario, we still see AGN. So that's the case for seeding of supermassive black holes. Now, as I say, this is such a rapidly evolving field with JWST. One of the really mysterious things that's come out of JWST are the little red dots. It's very hard to open up archive these days without seeing little red dots. If you Google little red dots, it's all medical. Okay? But you have to add galaxies on there to actually get the interesting. And the fun, and what are little red dots is these very compact objects at redshifts of 4 through to 8, with strange SEDs that could either be as obscured AGN or very, very compact star-forming regions. So the basic nature of them is still unclear. But one way or the other, there is a consensus emerging that there is a supermassive black hole there that's accreting. It must be doing it in some way that is quite strange. And one of the most compelling ideas right now is that they're super Eddington black holes, that they are small black holes growing at a very rapid super Eddington rate. One of the, there's a lot of them. So this is from one of the discovery paper, Little Red Dots, You see that in terms of the luminosity function, they're only really, an order of magnitude below that of galaxies themselves. This point, suggests that 10% of everything you're seeing at these redshifts are these little red dots. And they're not X-ray detected generally. They're X-ray weak. So one of the really compelling ideas here, and this is from Fabio, again, at the back there, is that if they are super Eddington black holes, that gives us something we can work with theoretically. And from running GRMHD models of super Eddington accretion, you actually predict that at some flux level, below that Chandra is currently at, there should be X-ray emission. There must be X-ray emission there. Even in so-called X-ray weak scenarios, which are low spinning super Eddington black holes. So Fabio's put the axis sensitivity there for reasons that I will share in a little bit. That line should actually now be drawn about there because of an orbit change. But still, you can see we're right in the ballpark where it's we should be able to uncover the nature of little red dots. Okay, moving on, I'll skip through some of this quickly. Another part of the PI science case is that of galactic feedback, with stellar feedback and AGN feedback. So this is from our stellar feedback case, looking at nearby galaxies. We can, the blue here is the axis simulation. We can pick out the X-ray emission from massive star clusters. We can actually, by looking at a set of nearby galaxies, we can do the luminosity function of several thousand massive star clusters in nearby galaxies and look at their luminosity function, and we can look for the need that is predicted in that luminosity function as you change over into a super bubble driven mode due to that need. In terms of AGN feedback, Chandra has done a huge amount of work on AGN feedback, especially at cluster scales, where you can see jets from AGN punching cavities and driving shocks in galaxy clusters. There's been some work done on individual galaxies with Chandra, but it starts to become a difficult thing because the hot baryons in individual galaxies the surface brightness is not very high. So with AXIS, we can start to look at whether these cluster-like feedback processes are operating at the level of individual galaxies in the CGM and hot ISM of individual galaxies. And these are just some simulations of that particular. So I forget which nearby galaxy we're simulating here, but you can see that with AXIS in this galaxy, we can map out the clusters, we can map out shock waves. This is in the temperature map here. We have enough photons to actually be able to map out shocks in the hot ISM of this galaxy. We can do high redshift clusters. So this is a particular cluster that's at 0.35 redshift. This is the Chandra data on it. Almost half a megasecond of Chandra. And you can see nice cavities there, the AGN blown cavities. Well, with Chandra, surface brightness really it drops off with the fourth power of 1 plus Z. So you put this out at redshift of 1.5 and you pretty much lose it with Chandra. The improved superior collecting area of AXIS, we get the basic structure of the cluster back. We can do spectroscopy of that cluster, we can look at its metallicity, and mapping out clusters, which we can go in principle all the way up to redshift of 3 with clusters. We can start to map out how the metallicity of clusters evolves with redshift, and this gives us a handle on the early enrichment of the IgM, because galaxy clusters are these buckets that just collect from the IgM, and the fact that they, even at low redshift, they're enriched so uniformly shows it's not just the galaxies in the cluster that's enriching it, it's being enriched from IgM fallback. So we can use galaxy clusters at high redshift as a tool to look at the very early enrichment of the IgM from the very early AGN feedback from blowing metals into the IgM. And this is a plot from our proposal where you can see that the axis points are here. These are current Chandra points. We can really map out which model of early AGN enrichment is the applicable one. Okay. our time domain science is an important aspect of access. And one of the things that really is I mean, it's not a new capability in the sense that Swift has it, but new in terms of the potential of putting that capability on an instrument like Axis, is that we have an onboard transient alert monitor. So if anything we're looking at our field, if a source flashes in our field, it is detected real time by referencing catalogues of sources. It's detected real time, and we telemeter that back to the ground in minutes, so we can push that alert out to the community. So, of course, this could be relevant for many, many areas of astrophysics. The one that we've focused on for the PI-led science program is supernova shock breakouts that we will be looking out, and if in our field of view a core collapse supernova goes off out to a redshift of order 1, so almost out to the peak of star formation, the X-ray flash as the supernova breaks free of the stellar photosphere, we should see, and we can immediately alert the ground. And then the duration of the flash, this is what this plot shows here, the duration of the flash, whether it's measured in tens of seconds or hundreds of seconds or kiloseconds, directly tells you the nature of the star that's blown up. And there's still a lot of uncertainty in which stars are blowing up, in which type of supernovae. So this gives us, so far there's only been one of these supernova shock breakouts ever caught, serendipitously, and we should be able to catch certainly over 50 and hopefully more like 100 in the life of our mission. Okay, let me skip this and just click to this. One other, in terms of the surveys that we're baselining for AXIS, I've talked about the extragalactic surveys, which will be our deep fields and then some wider fields, but also we're baselining the galactic plane survey, and there'll be roughly 100 square degrees of the galactic plane. So we look at this is not the whole galactic plane, don't be misled by this, but it's around the galactic center plus or minus 25 degrees or so. And the prediction is that there'll be something like 1 million new sources detected in this in this field. So a tremendously rich resource for all kinds of astrophysics. Our particular case here is we're looking for double degenerate accreting white dwarfs, so binary white dwarfs or accreting, which are the potential progenitors of type 1a supernovae. And literally, we should be able to actually measure the period and the period evolution during the phase of our campaign to see whether those neutron stars are actually going towards merger or not. Okay, now before I leave science and I talk about the project, let me just show a couple of representative kind of things that the guest observer might be doing. These are now not things that are part of the PI science case, not because they're not interesting, it's just because we have finite time that we can spend on things. One would be the impact of AGN winds, safer galaxy winds on host galaxy. This plot is actually Chandra, the soft X-ray gas, the purple stuff is a sort of super resolved image from Chandra. But what we're showing here with AXIS is that we can go into the system and actually carve out parts of this system where we've got a wind from the AGN that's interacting with the ISM with this host galaxy, and actually pull apart the spectrum. So the fact that we have good sensitivity and it's not LEM, but it's decent spectral response for a CCD down at the soft end, we start to pull apart the physics of what's going on here, the multi-temperature nature of it, whether there's a shock, whether it's multi-phase, those kind of questions. Stepping up in scale, there's a lot of very rich cluster physics you can do, of course, and we have a whole white paper full of this kind of stuff. So this is merging cluster ABEL 2046. And in this simulation here, we've shown that there's a bow shock in the cluster at this point. This is a merging galaxy cluster. Two clusters gone through each other. And with AXIS, we can actually resolve resolve the predictions for the width of the temperature jump across that bow shock that corresponds to the finite equilibration time of the ions and the electrons. So with Chandra, we can actually see the temperature jump. With Axis, we can look at it with enough photon counts to actually resolve that temperature jump and start to look at the plasma physics of equilibration across that shock. And then the final thing just to focus on is there's a huge amount of stellar work that will come from Axis, both with its sensitivity and its soft sensitivity in particular. Again, the point sources is always hard to show how impressive it is, but in some of these, if you put point Axis at, say, the core of the Carina cluster, there'll be tens of thousands of sources that you'll be able to detect. And what you can do with this is by pointing at a number of open clusters, open stellar clusters, we can now have a much, much better view of the X-ray activity of stars as a function of their age, as a function of their spectral type, and as a function of any other variable you might think. For example, spin rate, which might be an important one for determining the X-ray luminosity. So this gives us it'll transform our understanding of activity of stars across the whole gamut. And then with that, since these days it's relevant to exoplanets, with that you can take that knowledge of your star, know thy star, know thy planet. You take your knowledge of your star and see what implications are for your planets. And there's in the exoplanet community, there's this well-known Neptune desert. There's this region in the radius period plane where you don't seem to find many planets. And one of the ideas here is that this is basically extreme atmospheric loss. That planets that would be in this region around these stars have had their atmosphere stripped off by stellar activity. And so with our knowledge of stellar activity that will come from the X-ray observations, we can actually start to test these models. And this shows how, depending upon the X-ray measurement we detect, that you can look, evolutionary track of planets can be fundamentally different. Okay, let me just, if you go to our web page, and go through to, I think it's news and events, we have a long list of white papers. So if there's any science that I haven't touched on that is interesting, you can hopefully find a white paper for it. And of course, we're also working on a science book right now. Right, so let me now move to how we're going to do this, the actual the architecture of the mission and the technology. So, as I said at the beginning, the driving philosophy of Axis is to put the biggest X-ray mirror, the biggest high-angle resolution X-ray mirror we can on orbit for the budget that we have. So we're a single instrument observatory. We sometimes say we're simple because of this. Some people react against that word because there's nothing simple. But this is our basic architecture and our X-ray mirror assembly at this end, the XMA, and then at this end we have the X-ray camera module, which is the MIT Lincoln Lab CCD. So let me briefly just touch upon the detector. So this is the MIT Lincoln Lab CCID 100 chips, which are being fabricated right now. There's a test version of this chip, a prototype chip that was fabricated in step 1, the CCID 89. But these are chips with half arc second pixels, 24 by 24 field of view for a 2 by 2 Tyler chips. I say baseline is 5 frames per second, but we actually have every expectation we can go up to 20 frames per second. And like Chandra, we operate cold, not cryogenic, but cold. We operate down at -90. I think Chandra's a little bit colder than that. And then that's contained within an assembly, a camera assembly. And one of the things here for the Chandra aficionados, which is important, is that we are learning the lessons that were learned hard by Chandra. And given how important soft X-rays are to us, we have done everything we can to avoid contamination. So as many of you know very well, Chandra, there's contamination blocking filter here. This is also where you have your aluminum layer that stops optical light. And that's cold on Chandra. And that became a place where a lot of contaminants condensed on it and has been affecting the soft response. So learning that lesson, we're having a warm filter. We keep it warm. Plus we have other things to try to avoid contamination. We've got little cold fingers in here that try to suck any contamination that makes it in. So that's the main lesson we've learned there. And this whole thing sits on top of a focus mechanism. So just to show you some test data, this is test data from the prototype chip from MIT, and we're already achieving the baseline requirements on our spectral resolution. So, so the detector is in hand. Now let's come to the mirror. The mirror, of course, is the heavy lift here. And as I said, we need to break the scaling of Chandra. We can't have a mirror that is similar in mass per unit area or cost per unit area to Chandra. So the fundamental philosophy here that's driven us to the single crystal silicon optics is that we're leveraging off the semiconductor industry as every way we can. So the very existence of this substrate, the very existence of this material, the single crystal silicon, is due to the semiconductor industry, and that this wasn't possible in the Chandra days. We've now got this material that is very stable. You can make mirror segments that have very low internal stresses, and then as important is that the machinery you need to work with this material is now commercial off-the-shelf machinery you can buy from the semiconductor industry. Okay? If you have to make your own machines, that's very expensive, and I was never privy to the details, internal details of the Chandra budget, but I've been told that a lot of money in Chandra went to making the machines that made the mirror, and so as much as possible we have to avoid that. So we're leveraging these huge investments by the chip industry in this. So beyond that, the other principles we have for the XMA is to have as much as possible a modular design. So this enables you to have parallel production processes for your mirror as you're going. Both parallel production processes, then of course this is NASA, they want everything to be qualified and tested and the like, and it's much easier to qualify and test things at module level and then say you're reproducing that n times than it is to do that at the whole assembly level. And say maximize use of commercial off-the-shelf machine. So you've already seen this, which is the basic substrate we're using. This is then the basic architecture of the mirror. So those mirror segments get stacked up into mirror modules, which are like this. I'll talk about this particular module design in a second. These mirror modules, this is where the precision alignment has to be when production of these modules. This mirror module then forms a little X-ray telescope all by itself. Okay. And then you take that mirror module and you put it into an array, into your array, like this. And the tolerances of putting these into the array are actually not that restrictive. And then you embed this in your supporting structure. This is the supporting structure for the modules, and then all the other stuff, light baffles, thermal pre-collimators, thermal post-collimators, all the stuff you need to make the mirror work. Let me just show you a little bit of this. Is actually pre-phase A work, just to show you that some real pictures. This is relatively old now. This is one layer of mirror, one pair of these silicon mirrors that has been aligned, bonded and aligned, and this achieves 0.8 arc seconds. This pair of mirrors. And so this result is actually a little older now. And this is the basic way that you line these things up into modules. You actually use these hexapods, and they line these. They construct these segments into modules, and then this is a particular test module that Will had, not for Axis. This is actually for a Bloom program several years ago, and again, this test module achieved good results. So let's come to what we've been doing in phase A. So we're currently in phase A for Axis. And the top level schedule is this. So the phase A started in November. On the 18th of December, we have our concept study report due. This is the step 2 proposal. This was originally November, but the fires in California affected our competitor Prima quite badly because of the JPL. So NASA delayed the deadline by 5 weeks due to that. And then the expectation is we have a site visit in April and the selection we announced in June. And then the launch readiness date right now is no later than July 2032. So the guiding philosophy for our current work we're doing right now, is reduce risk, do everything we can to reduce the risk on the mission, and focus on what I call the heavy lift, which is the mirror. Yes, the heavy lift is the mirror here. And so this means that in phase A, we're focusing on maturing the technology for the X-ray mirror, and as important, demonstrating it's actually manufacturable. For example, with links, one of the major hits we got was the manufacturability of the mirror. Even if we proved the mirror was doable, we still had to be able to manufacture it. And so because of that, every trade decision we make, every decision we're making in the project right now is to try to make life easier for the mirror, understanding that's the tall pole here. So let me just share a couple of examples of what I mean by that. In our step 1 proposal, this is what went in November 2 years ago, this was our module design. We had these pairs of mirrors which were stacked up like this, and you can get the sense that the pairs are stacked very close together there. And the minimum separation pair was 1.5 millimeters. And this was done on the assumption that you can build this up, you put a pair down, you can you put a mirror down, you bond it, you bake it, bake the bonding, and then you adjust, and then you put the next mirror down, bond it, you bake it, adjust. We would recognise that was a problem to build it up like that. There was a risk there that if you're baking the system many times. So we've moved to this new design. What we've done is essentially take our X-ray telescope and sort of pull it apart like that. So we've got just the same number of segments essentially, but now the pairs, this primary talks to this secondary, this primary talks to this secondary. But so it's 2 X-ray telescopes, if you like, that are just sort of being pulled apart. But now, for the same number of segments and the same affected area, in fact, if anything, slightly more affected area because we're not getting as much shadowing, we've increased the separation to 4 millimeters. And that's actually enough now that they've demonstrated that you can basically bond the stack up in one go, bake out all the epoxy as you need, and then you've still got enough space to go in and adjust the flexures, align to precision alignment of the whole thing, and you've got enough space, literally enough space to work with this. This all gets very practical, but it is all very practical. You need to have physically enough space to stick screwdrivers in, sort of. Not the kind of screwdrivers in my shed, but so that retires a major risk that had been identified in this mirror. So moving ahead with that design, this is a test module that we are currently building. The idea is that if you go back to this one, each one of these mirrors is actually a slightly different optical form. Okay, so you need each of these mirrors is a slightly different shape. It has to be exactly the right shape for its position in the mirror array, and you need the right shaped mandrel, circular thing that spins. You grind it on. I'm a theoretical theorist, so that's my circular thing that spins. You grind on. You need exactly the right shape of it to be able to form this. The mandrels are expensive, right? So we don't have the phase A budget to build this entire thing, but we don't need to because you can demonstrate everything you need to demonstrate by building this, which is you build three layers of segments on the bottom, 3 layers of segments on the top, and in here you have mass dummies. So you have things which are just the same mass, actually the same thermal inertia as well in here. And this is what we're building right now in Will Zhang's lab. He has the manuals delivered, he has the silicon he needs, and within hopefully 2 months we'll have our first one of these modules, and then we'll have one every month after that. And that will demonstrate, and then we'll put these in X-ray testing, and we'll demonstrate that we can achieve the axis requirements from that. And that will, to a very large extent, retire the direct technology risk. We've brought new partners on board to help us with this. So the testing of these modules, of course, is not something that is trivial. There is a facility at Goddard, there's a beam line at Goddard that can be used for this. But in fact, there's a much more effective facility in Germany, Panther, and Max Planck Institute, MPE, has now joined the Axis partnerships. So we're planning to do our X-ray testing both in phase A and in actual development at MPE. And then we've just recently brought on 2 industrial partners to lead the manufacturing plan, and if we're selected, the actual manufacturing of the mirror. So Coherent, which is formerly Tinsley, which is a company that's known well to many, they're leading our manufacturing segment, and then Blue Halo is leading our module assembly. These are 2 extremely capable companies that have had a lot of expertise in both astronomical instrumentation and, of course, instrumentation in many other fields of life. And then coming towards the end, the other big trade study we've made recently is our orbit. So our step 1 orbit was low Earth orbit, a low inclination low Earth orbit. So low inclination because we wanted to avoid South Atlantic anomaly, be as good a radiation environment as possible. Low Earth orbit because that provided good comms for the time domain science. There are many things that make low Earth orbit a problem, and for example, with any precision system, and an X-ray mirror is no different. Thermal stability can be a big problem. You don't want your mirror heating up and cooling down because that makes it expand. So if you're in a low Earth orbit, continually cycling from daylight to night side of the Earth is a big warm thing that's spinning around you all the time. Your thermal environment is very dynamic. So because of that, we did quite a careful trade study, and we've decided, this was literally just 2 or 3 weeks ago, to shift our orbit to Sun-Earth L2. And this is a much more stable, the guiding philosophy being make life easy for the mirror. This is a much more stable thermal environment. We don't have to worry about complicated light baffles to keep the bright Earth out of our beam. We don't have to worry about orbital debris, which is becoming scary at an increasingly alarming rate. I was really worried that if we stay in low Earth orbit, we'd get into phase B or phase C, and then NASA would come down with a directive that there should be no LEO orbits satellites. So for all those reasons, there was a very strong desire to push to a higher orbit. And then it turns out that there are actually perfectly affordable commercial communications options for L2. So that we can still maintain our time domain science by going commercial at a rate that is affordable to us. The downside of not being in low Earth orbit is there is increased background. So this is these are our background curves for axis. So in the soft X-ray band, we're actually dominated by the Milky Way. The Milky Way in the hot bubble, local hot bubble. But the non-X-ray background, the particle background that is inherent from cosmic ray strikes in the detector, does increase as you go to L2. So there is a hit there on science that is very low surface brightness science, or science where background is a limiting issue. But on the flip side, we now don't have the Earth in the way, so your time domain science can become a lot more compelling. Okay, so let me wrap up here, and so I want to leave a little bit of time for questions. Put up this. So remember, everything I talked about, we're fundamentally building an observatory for the community, and that is a very strong driving motivation for us. So we're trying to make it as easy as possible for the community to get involved. Scan that. That'll take you to the Axis webpage. You can join Axis Science Working Group. We currently have a process open for putting together our Axis Science book. So basically, it'll be a sort of set of example guest observer cases. And we're planning a community workshop in Annapolis in mid-May. So at that point, I will wrap up and take any questions. Thank you.
Okay, so thank you very much, Chris, for this overview. So we'll start with questions online. So if anyone online has a question, please raise your hand using the React button in Zoom, and then feel free to unmute yourself. I will call out your name if you have any questions. We'll just give someone, okay, no, you're receiving a round of applause online. No questions yet. Does anyone online have a question? Okay, not for the moment. So any questions for Chris in the room? Yeah, Rafael, sorry.
Thank you, Chris. For the time domain aspect, so you said you will have relatively quick response when a transient is detected. If such transients are detected in a geo observation, for example, will you need to negotiate with the PI of the observation so that data can be released?
So that's a good question. The current thinking is that the transient. Yeah, the current thing is basically no. That if there's a transient in the field, the alert goes out immediately. One thing that's driving that, and this is not by any means an Axis level decision. This is Congress. Is that the notion of proprietary time is essentially going to go away, and that's the assumption we're operating under. So we're operating under the assumption there will be a mandate to get all data out to the entire community as soon as possible, whatever that means. Yeah, there'll be some pipeline processing thing. So presuming that's going to be as applicable for transients as it is for the primary data. It is an interesting question though. If you happen, it seems a bit unfair that if you happen to be observing and there's a really interesting transient, you wouldn't get first dibs on it. But of course, the whole point is to get the community on target literally in minutes, and so it's not consistent with any level of negotiation.
Great, so we have a question online from Margarita. So if you want to unmute yourself, feel free. If not, I'm also happy to read your question.
There I am. Can you hear me?
Yes.
So, hi, Chris. I'm involved with Axis with one of the science groups, but my great interest is in improving the PSF, going really to sub-arc second resolution. We've done that with Chandra. I mean, the resolution we say it's 0.5, but we have been able to reach by using data information and so on, and defining the PSF, we've been able to reach basically HST resolution. And one option is to do data, like what we do with with Chandra, and he use SER type algorithms. But I've used a lot the HST with control data, where you go, shift, and expose. Move half a pixel or quarter a pixel and expose, and then combine those images together. I'm using my hands, right? I see my anyway, combine those images together to reach, for HST, we'll be able to go to 0.02 arc seconds. And for Chandra, definitely 0.1 arc second, whether it is stellar sources or AGN, one of the AGN that you showed with Pepe Fabiano and so on. So would be would that be a possibility?
Yeah, so no, thanks. That's an interesting question. So, yeah, our pixels are half an arc second. Um, of course, our PSF is a bit worse than Chandra. So in some sense, we are actually sampling the PSF more effectively than Chandra does, which on the flip side of it takes some of the power of the dither technique out. The two unknowns here, of course, are, and hopefully these will become knowns sooner rather than later, are, how much better than our baseline can we do? Once Will has these test modules built, can we achieve what we think our current best estimate is of 1.2, or can we even beat that? I'm not making any promises, but I would love to do as well as possible. And then even beyond that, what's the true shape of the PSF? Do we have the core that many missions do? We've got a different mirror architecture to many missions, so we have to do the hard work of ray tracing that through a full model that includes thermal distortions, etc., etc. But we may well have a core that does appreciably better than even that baseline number suggests. So I think we will have dithering, and that's already part of our plan, just for the, especially, we're not going to have a pixel by pixel calibration map, okay? So we have to dither so we can have reasonable calibration of our spectra, and we'll have sub-pixel information in the same way that Chandra does. So certainly there should be all the information you need to try to squeeze those last little bits out of the data.
Great. Grant has a question.
Thank you.
Thanks, Chris. Great talk. Can you give a comment on what NASA might expect for the CSR in terms of your commercial comms partnership? So presumably you're essentially renting commercial dishes, presumably also around the planet, for 24-hour coverage. You can't sign a contract in Phase A, so is this a handshake, an MOU?
Yeah, so what we see is if we can get some company to issue a basic ROM to us, a basic rough order of magnitude to us, that's probably what's needed for the CSR, for the Phase A. I mean, you just have to show that there's multiple. You have to show proof of principle. It's not going to be a problem.
Any other questions for Chris?
It's kind of a naive question about the mirrors. You increase the gaps. Won't it make you prone to more scattered light, stray light, and all these increased background? Or can it be baffled?
You'd have to baffle it, yeah. So it changes the design of the straight light baffle. Yeah, you're right.
Okay. Any more questions upstairs from the room or on Zoom?
I have a quick question about bright sources. You mentioned the full frame on one on side. What kind of window modes do you have? At what stage does pileup become problematic?
Yeah, great question. So I mean, the current baseline, if you sort of just roughly run the numbers in your head, the pileup limit is very Chandra-like. Because we have 10 times collecting area, but we roughly read out 10 times faster. A little bit better because we sample the PSF. PSF is bigger, so we sample it better. So the kind of window modes we expect, again, will be very Chandra-like because it's the same basic CCD technology. So we expect to be able to do subarrays and read out potentially up to hundreds of frames per second if you subarray down. So certainly, I love bright sources. Even at CCD resolution, I love having high count spectra. So we'll do everything we can there, and if we can increase the baseline readout, we'll do that too. So.
Chris, I wonder if you guys have gone through a trade of making segments thicker, substantially thicker than they are.
So in step one, there was original segment thickness was less. It was half a millimeter. And we went through that trade, and then we made it 0.8. So you always keep it in your back pocket. If you have to, you could go thicker. So far, it doesn't seem like we need to. If the first of these test modules pops out and we find we have a problem, that will be a place to go. Is to go to thicker segments. But right now, it doesn't seem like there's a strong need for that, because you pay the price in literally geometric blockage of your. So you pay the price in effective area.
Extend it to 4 millimeters.
Any final questions for Chris?
How do you do the station keeping at L2?
You mean how do you stay at L2? Yeah, I mean so
It's not an exact orbit,
it's not an exact orbit. So Northrop has run the numbers, and you need very little delta V to actually stay there. It's well within the capability of.
You need a precise in-track measurement. That's the difficulty.
The more precise your in-track, the better you do once you're there. But again, Northrop has run the numbers, and if they're assuming standard launch vehicle accuracies, it's actually not a problem. In fact, they believe that compared to our step 1 proposal, we can probably get rid of half the propellant we have, because we don't need it. So if we don't do that, we keep that propellant, we have a lot of options.
Okay, so with this, we'll finish the seminar, so thank you very much. See you next week.